We just saw these limit laws, which say most of the time limits work the way that you would like them to. We're going to talk about one scenario where something fails in these limit laws. In order for these to work, our limits have to exist. So what I want to talk about now is a limit law that works when a limit does not exist. We're going to talk about, in particular, the squeeze theorem. So what's the setup? I've got some sequence, it's these pinks, and it has some limit, whatever this dotted line is. And then I've got two other sequences as well. One is these blues, and one is these blacks. And they have a particular relationship, which is that at any given point, for the first or the second or the third, I choose which index, let's say the fifth term of the series. Blue is smallest, black is in the middle, and pink is on top. And this relationship holds for the sixth term of each sequence, for the seventh term of each sequence, and so on. So we say the black is kind of sandwiched in between the blue and the pink. The squeeze theorem is also sometimes called the sandwich theorem. You can also say it's squeezed between the blue and the pink, because if the blue and the pink go to the same limit, so as you can see in this drawing, the blue and the pink are both getting really close to this dotted line, then the black has to go there as well. It's got nowhere else it can go. It's not going to be smaller than the blue, and it's not going to be bigger than the pink, and the blue and the pink both go to the same place. So that means the black has to go to that place as well. If we look at what the theorem says in the context of that discussion, these are my three sequences, and they have this relationship that at any given term, I know which one's on the bottom, which one's on the top, and which one's in the middle, and that order doesn't shuffle. And I need the top one and the bottom one to have the same limit. If the top one and the bottom one have the same limit, then the middle one, Bn, has that same limit as well. Let's see this in action. Let's say I want to evaluate this limit. It looks like I should be able to use those limit laws like in the previous video, but there's an issue. I want to break it up into pieces, but this limit does not exist. The limit as n goes to infinity of cosine n doesn't exist because cosine n just keeps bouncing around. It's not getting closer and closer to any one number. It's bouncing all around, so its limit doesn't exist. That means I'm not allowed to just kind of break this up into its constituent pieces the way we did in the last video. So although this limit doesn't exist, I still know some stuff about cosine. In particular, even though the limit doesn't exist, cosine isn't doing anything that's very interesting in this context, because no matter which term I'm looking at, cosine of n is always between -1 and 1. Doesn't matter if it's cosine of 1,000 or cosine of 1, cosine of anything is between -1 and 1. So using this, I'm going to be able to replace this term in my sequence with a 1 or a -1, and that's going to give me my sort of three sequence sandwich, one on the top, one in the middle, one on the bottom. Let me show you what I mean. Cosine n is always between 1 and -1. So that means 2n plus cosine n is always between 2n plus 1 and 2n minus 1. I've just taken this inequality on the top and added 2n to all pieces. And now I can take all pieces and divide by n plus 1. N plus 1 is positive in this context, and so it's not going to flip our inequalities. So I take this number, 2n plus cosine n, divide it by n plus 1. And that's going to be less than or equal to 2n plus 1 divided by n plus 1. It's going to be greater than or equal to 2n minus 1 divided by n plus 1, because I just took each part of this inequality and divided it by n plus 1. Now we have our sandwich. The one in the middle is the one I want to know about. The ones on the ends, I can find their limits. So if you remember, these are rational functions. It's a polynomial over a polynomial. The fast way is to say the top and the bottom have the same degree. They're both degree 1 polynomials, and so the limit is going to be the ratio of their coefficients of the leading terms. So the coefficient of the leading term on the top is 2. The coefficient of the leading term on the bottom is 1, so this limit is 2. The slower way to do the same computation is to divide the top and the bottom by n. So this is 2n plus 1 divided by n plus 1, and I can multiply this by 1 over n divided by 1 over n, so I'm not really changing the function. Then this becomes the limit as n goes to infinity of, on the top I get 2 plus 1 over n, on the bottom I get 1 plus 1 over n, and as n goes to infinity, 1 over n goes to 0, and this is the long way of seeing that our limit is 2 over 1, which is 2. So that's the limit of the right-hand side. This sequence is going towards 2 as n goes to infinity. Why don't you take a second, evaluate the limit of the left-hand sequence, and then figure out what that means about the limit of our original sequence. The left sequence is very similar to our right sequence. The top and the bottom have the same degree, so our limit is just the ratio of those leading coefficients, which is 2. So in the context of the squeeze theorem, this really is squeezing. As n gets bigger and bigger, these numbers get real close to 2. These numbers get real close to 2. And these numbers are always squeezed, squozen. These numbers are always squozen in between. So they have no place to go other than 2. So here's how we can write that. For all of my indices, the terms of this sequence, 2n minus 1 over n plus 1, are less than or equal to the terms of the sequence we care about, 2n plus cosine n divided by n plus 1. And these are less than or equal to the terms of the sequence 2n plus 1 divided by n plus 1. And the limit as n goes to infinity of my lower numbers, 2n minus 1 over n plus 1, is the same as the limit as n goes to infinity of my higher numbers, 2n plus 1 over n plus 1. And that number is 2. So, by the squeeze theorem, that function in the middle, 2n plus cosine n over n plus 1, it's in the middle, it's got nowhere else to go but 2. Again, the reason we had to use the squeeze theorem is that this piece doesn't have a limit. So I can't just say, oh, the top goes to 2n plus 1, or the top goes to 2n minus 1. Because it doesn't have a limit, we need to do a little bit more work than just using the limit laws that we saw in the last video.